I did bring you to class. I would never give a midterm after a distance lecture. We would always review before the midterm. So we're going to review today for the midterm. So I've been posting homework solutions. I did a video with homeworks 1 and 2. I'll take questions or I'll hit highlights about that. And then I've got this up on Carmen for homework 3. So basically I'm going to go over that today. Mainly today I'm going to focus on the things that you need to know for homework 3. And then because we're mainly just reviewing concepts and going over things, and I don't know how much you want to memorize, I believe memorization is a good thing. The more you remember, the more creative you are. But we all know exams have nothing to do with creativity. It's just, can you reproduce the answers that, the only answer that the question is asking for. So I'm allowing you one sheet of notes, 2 sides. Okay. No 3D cheat sheets. I've had people do one sheet of notes with Post-it flaps. So you can write underneath the flap, on top of the flap. So 2D sheet of paper both sides. You can have it. And then I do have the homeworks graded here. They're in alphabetical order, so I'll just pass them back while we're going through class. All right, so Wednesday we'll do the exam. Friday, since it's the Friday before spring break, that isn't asking for a distance lecture. I don't know what is. So I'll just go ahead and keep making videos and pointing out the content. And then after spring break, we're really going to start doing some testing. So I've got all the equipment in. I think I have some good ideas of how to use it. And so we'll set up some, instead of meeting in class, you'll be meeting as a group with some hardware, doing some testing of op-amps, data converters. And our digital testing will be restricted to the launch pads and the Arduinos as far as the digital I/O of that goes. Okay. So shields seem to be doing okay, and then we have the so you'll have a shield, you'll have the Analog Lab System Kit Pro. How many of you have an Arduino? Uno? Okay, that's pretty good. So I will put each of you in charge of a group. I'll supply some Arduinos, but if you have your own, then just use your own. And then our testing software will be the Arduino Energia IDE. So I will talk a little bit about that after the exam, but basically it's a nice way to write software, and it's consistent with the notion of this is facility equipment that you have access to, versus we don't have big testers here that we have access to the type of software they need. Okay, so the on the content then, I've added the homework solutions that I'm going to go through today, and then I've put up one video for H1 and H2, and tonight I'll make a 15-minute, 20-minute video for H3, and we'll be set for the exam. So for those of you who haven't had me in a course before, I like to ask concept questions as well as calculation questions. And in this course, there's more concept questions, even more. So typically it's a 3-page exam. The first page and a half might be concept questions, and the second page and a half, or the second half, 50% of the exam will be calculation type questions. Right? And it'll be either INL, PNL, or some type of modeling question in terms of the comparators that we've been looking at. So DAC equations or gain equations or things like that. Any questions? All right, so So on the video, I did 1 and 2, so I'm going to do those last. I'm going to go backwards today and start with 3. But basically, I explained, for example, this question on the video, and the simple way of it is basically the signal is 16 times too small for the B route of the ABC. Now there's multiple ways of calculating SNR, depending on whether you use amplitude or RMS, and that causes some slight differences. As long as on the exam you state, this is my way of calculating SNR, and this is the way I'm going to do the problem, that'll be fine, as long as it's logical in some way. No imaginary numbers like that. And then I found some nice things for looking at ferrite beads and bypass capacitors. For the ground plane, it turns out Analog Devices has a nice layout thing that I just found over the weekend. So I would look at that, and I'll make some comments about the ground plane idea as we go on today. So I think I have it up here. So high-speed printed circuit board layout, and if you go through this, you'll see the things we've been talking about: bypass capacitors. The idea with bypass capacitors around op amps. Now this is overkill in terms of the inductance that you're worried about. So it turns out that we have a pretty good intuition of capacitance. But what about the capacitance of a wire? Okay, so if we have parallel plates, we have an easy way of calculating the capacitance. But if it's just a wire coming to a ground, then it's a lot more complicated to calculate. So we want to have this notion that if we have wire, such as the power lines, because after all they are wires, right? And it turns out that I have a capacitance in parallel per unit length. So this is CL per millimeter. And typically we ignore it. Now, the curious thing is if we have a ground plane close to that wire, here I'm going to have a ground plane. Then it's unclear if you're still ignoring the capacitance, because now you have a well-defined capacitance. Okay? But really, it's going to depend on whether this is attofarads, picofarads, or nanofarads. So when we're talking about wire capacitance, those are the prefixes that we're looking at. Now, the other thing that we have with the wire is it has some inductance. So this is L per millimeter. And it's fairly tricky to calculate that inductance because it has to do with where is my loop. So remember, inductance is about a loop of wire. And even if it's not looped, then there is a single loop between it and the ground plane. So what we'll see is that typically we have an LDIDT, and this is of more concern to us than the straight capacitance. So we're going to get a voltage drop due to this LDIDT, and we're typically worried about that. And it turns out that we talk about a distance here, D, then as D decreases, what happens to the capacitance? It goes up. But what happens to the inductance? Unclear, right? But our rule of thumb is that inductance depends on cross-sectional area. So here I have some area. So our rule of thumb is going to be that as D decreases, L decreases. And so that we're mainly using a ground plane to control L. So as you look through the online material, look for how inductance is calculated in terms of next to a ground plane and next to a wire that's ground, or a point that's ground. And basically, you want to come up and there's the concept of straight capacitance and straight inductance. That's fat palms. So that's what you're looking for, right? So typically, when we have a ground plane, we're removing stray inductance for controlling the LDI/dt curve. And then when you add bypass capacitors, we're looking at a resonance frequency that's between the stray capacitance and the stray inductance to sort of minimize the, we don't want to, for example, happen to have our power lines have a, hang on a second. We don't want to have our power lines happen to have a resonance frequency at our cell phone or anything like that. Because all you've done there is you've taken the radio wave coming off the cell phone and amplified it. Okay. So we will pick capacitors. So that's why bypass capacitors do not have any random value. And that's why making them bigger is not always the right thing to do. Questions?
Do you usually worry about the one-side capacitance layer that they play with different systems?
Yes, you do, but we do this in kind of a priority order, right? So, for example, on the TI board, none of these concerns are there. There's no ground plane, there's no ferrite beads, or another name for a ferrite bead is called an RF choke. So we want to choke off the RF voltage. So it really depends on the application. Okay? And as someone pointed out, that I could always do these things and improve them, it just costs more. Right? So engineering is always about cost. So as you look at this material, that's the kind of calculations that are talked about, and for us, we're just going to be aware of them as a concept. Ultimately, we will worry about these stray voltages in relation to things like the offset voltage of a comparator. So you did do calculations, or I showed on the video, that by increasing the gain of the op-amp, we were sort of controlling what the softness of the comparator trip voltage was. So those kind of things interact with these kinds of things, and you almost have to do it on a case-by-case basis. All right. So basically, the multiplier, I'm not going to say too much about. You won't have to worry too much about it. I will say that I did add the data sheet for the multiplier with the TI data sheet. And All you need to know about a multiplier for now is that it's useful for looking at frequency domain. Basically, the trig identity is sine times cosine, is the sine of the difference of the frequencies and the sine of the sum of the frequencies. We low-pass filter so that the sum goes away, and we look at the difference term. You'll see that we haven't talked about it yet, but we'll want to hook up, if one ADC is good, then multiple ADCs should be better. So one way for us to increase performance is, these ADCs aren't that expensive. Already on processors, we're putting multiple cores where you'll have maybe 16 cores on a processor. So why not put 16 ADCs and hook them up so that they work together? And we'll see that clocking is the reason why not. So clocking is going to be a problem for us, and we'll look at the simulations of the DAC ADC that we've done in top spikes and see the problems that we have largely in that is because we don't have any clocks for the ADC and we don't have any clocks for the DAC. So it's asynchronous. Now, some of you know I love asynchronous stuff. To me, the big difference between how we build element 14 electronics and how biology builds carbon-based electronics and carbon and blue that biology doesn't use clocks. Biology doesn't tell there's no clocks. So how a trillion gate system works in biology just boggles my mind. It should not work. You should not be here understanding what I'm saying. And so the ability to build electronics without clocks, to me, is sort of the grand challenge that's ahead of us. And even ADCs and DACs have to be clocked. So not only does the digital have to be clocked, but the converters have to be clocked. And then we'll see that when we talk about the pipeline ADC, in here, for example, we'll see that it needs to be clocked on the analog side. But clocks are very expensive, so if we could build electronics without clocks, we would make a lot of money. But it seems to be a very hard thing to do. So I'll do this mainly on the video. Basically, the number of inversions in the loop I'll do today if we have time. But you should understand that I need an odd number of inverters in the loop. And even if it's one inverter, then it has to be an inverter. And I can either put the inverter as a capacitance charging a virtual node, so that's a negative SRC, or I can put the inverter in the Schmidt trigger, or I can put them in both. If I put them in both, then I have an even number of inverters, so that's a concern. I think this problem has worked out really well in the material. So basically, I reference this chapter 15 from Johns and Martin, so that's this chapter right here. And if you go through the material there, we'll get to the INL, DNL problem that we're doing. Basically, you're just following this, but you're doing it with slightly different numbers. Does anybody have any questions about that?
So should we expect anything different since offset is kind of removed from the equation when we do INL?
So your numbers will be slightly different. It turns out the offset error here is the biggest error in the DAC.
So we don't subtract 11 millivolts from all those values?
Yeah, you don't subtract 11 millivolts anymore from all those values. So your gain's going to be different because it's not there, and this .022 is not going to be there.
Yeah.
Okay. So that's the main difference.
So we don't take offset, we just subtract from the first value, not all of them?
No, there is no offset. So,
Yeah.
right. So that's a better way to put it. So this first value is .000. Thank you. Well, then you're back to the same problem.
That's,
right?
yeah, that's
So that's not what I want you to do. I want you to get different numbers. Right? So otherwise, you're just doing the same exact problem, you get the same answer. So for me, the easy way to make you do different numbers was to change the offset to 0. Correct. Correct. So only the first value alone is 0. So I'm not asking you to do that part, but for the modified version of it, since we have no offset error, the absolute and relative errors are the same. They're in the INL. So you still pick the maximum INL error and use that. It just happens that when you remove the offset, INL will not show the offset anymore, right? Because this value here is automatically put to 0. Right? Now I do want you to understand this concept here, and let me show you where this is in the notes. And we did that in the video. But in the notes, when we talked about, so I could ask you about accuracy and precision of a DAC, and you should be able to tell me what it is. So here's this DAC, and we drew this bounding box. So the size of this bounding box in this problem with the offset is 11 millivolts. And so I want to know how much does that correspond to in bits. So I have a 4-volt reference, and I have 11 millivolt error bar. And so when I turn that into bits, it tells me I have 8.5 bits. So my accuracy of this absolute accuracy, rather than coding it in voltages, I'd rather code it in bits, because my reference voltage can be different. So I have a 3 or 4-bit DAC, depending on which problem we're talking about. In this case, a 3-bit DAC, but I have 8.5 bits of absolute accuracy. However, that absolute accuracy is goofed up because the error is in the offset. So if I don't have that error, and I'm looking at the error across these, then the biggest error is 0.007 LSB. The LSB is half a volt, so that's 3.5 millivolts. And I do the same thing, I change this to 3.5 millivolts, and then my accuracy is 10.2 bits. So you can see that just like SNR, some of this gets kind of subjective. You know, am I going to worry about absolute accuracy? Am I going to worry about relative accuracy? These are just guidelines. These are not performance or requirements that I can easily map to a system. But we'll see that one of the reasons that we don't build frequency domain DACs and frequency domain ADCs is we have a much harder time defining what the absolute accuracy is or what the relative accuracy. When I talk about a frequency and I say I have an error in frequency, I can't say that I have an error in frequency at a specific time. Why not? I can't define frequency over a specific time. Right? So I have to start being a little fuzzy about it. Okay? So I have to use fuzzy type sampling, or sampling that involves interval, not a specific time. My story is this is how biology does sampling. You have no clocks, you don't see clocks. Biology does self-time sampling. How it does it would be great to know. One way to do it, to figure it out, is to think of it in theory, and then maybe you'll stumble across the same way biology does it. Because I'm guessing it'd be pretty hard to dissect somebody's brain while they're alive and see where the clocks are. It's not likely to happen. So this is a clue for the R2R ladder. So basically, you start at the LSB, and you're doing parallel combinations of 2R to 2R to get R, and then you're adding that R to another R to get back to 2R. And basically, the voltages at the top of the ladder are weighted by power of 2. This one I'll show when I run top spice. This one here, I would go ahead and look how pipeline ADCs work and then look to how you change the code to make it work like a pipeline ADC. Okay, so let's look at pipeline ADCs for a second. So Nyquist rate data converters. So the idea behind a 1-bit pipeline ADC, which is what our model is we have a single comparator, which is what you've been working on. And that comparator controls a switch, which either adds or subtracts back a reference value. Now, what you want to understand is this is a bipolar plus or minus supply pipeline ADC. We're using a single supply pipeline ADC. So instead of having Vref over 4 and minus Vref over 4, our two values are what? 0 and Vref over 2. Okay, so, and basically all we're doing is, as we go through these stages, and I'll show this in the video. So in our code, we have a 4-bit DAC, so it's a 16. If we made the reference value 16, then each LSB is 1 volt. So in here we have our comparator, which is either high or low, depending on whether we're in the top half or the bottom half. So the way a pipeline ADC would work versus the way our ADC works is, let's say that we're at 16 to 0, and basically we're going to use a reference of halfway, which is 8. And if our value was here, then we stay in the bottom half, because basically D out is 0. If our value was here, then D out, D is 1. But then I subtract away 8, so then I'm back in the bottom half. Okay. So then I go to the next stage, and now my reference level would be 4. If my value was still below 4, then my next bit is 0. If my value happened to be above 4, then basically this is brought back down to the bottom half, and my next bit is 1. So that's how our code works in top spice. We always go toward the bottom half of the interval. So 8, 4, 2, 1. In a pipeline ADC, what's the difference? The pipeline ADC is I'm going to still do the subtraction, but then I'm going to blow up this interval by a factor of 2, so it's back to 16 to 0. And then my reference value, instead of having to be 4, will now still be 8. And then the next stage, since now I basically got this problem repeated again. So again, if I subtract to the bottom half, either from the top or the bottom half, I still multiply by a factor of 2 and go back up to 16. So the advantage of a pipeline ADC is the reference values don't have to change. And building that reference value and making it stable and accurate is the hard part of an ADC. So that means when you change your code, what do you want for n bit here to be in all cases? 3, that'll give you 8. Make sure that you put that down here too, in the LSB, okay? And then I need to go ahead and take the output of this diff circuit, which is always going to the bottom half, and blow it back up to the full scale. So I'm going to multiply by 2. So I'm going to make sure that this diff is multiplied by 2, which means I multiply in by 2, and I multiply this by 2. So in the code, how do I make that happen? Here's this diff, poly 3. I want this to be twice as big now as it was before. So I have to change these coefficients to be 2. And make sure you change the right ones to be 2. Okay? Any questions on that? And if you run that, then you should see no difference between the way this code runs now and the way the code runs when you made it more like a pipeline DMC. And I'll show that on the video. Any questions on this? Okay. So let me go ahead and show you the ramp rate idea. Okay, so it turns out this time here doesn't really matter. We could make this 100 nanoseconds, we could make this 100 microseconds, we could make this 100 milliseconds. There is no clock. Now, I'm going to ask you, in the DAC 7821, how does the clock work? How do we clock in the data? That's part of the homework that you did. We'll go back to that. But just a reminder, we're using the chip select signal on the actual DAC to clock in the data. Okay. If you look at the data sheet, you'll notice that there's a data valid window time. Right? The data has to be ready a certain amount of time before the clock. So those kind of issues, we don't know how to build electronics unless we do things that way. So this is the one where I think I've already cleaned it up like I left it on the video. Yeah, so if we look at the comparators, I've made their gain higher. I've made the, in a sense, I made the offset voltage more controlled by increasing these to be a much higher gain. So in the video, we showed that that's what got rid of the blitzes that was here. And it happened because of the way the data was being brought to the DAC, because the DAC is not clocked. So notice this LSB toggles on and off constantly. Why is that? Because I'm just counting up in digital. So as I count up, this goes 0, 1, 0, 1, 0, 1. So this ramp rate then is related to the period of this P1. So if I asked you how many LSB are in a period of P1, you would tell me 2 LSBs, 0, 1, 0, 1, right? And so one LSB then has a certain amount of time. So here we can see that it's a little under 5 nanoseconds. Notice we have some asymmetry here. Okay, we can talk about where that asymmetry comes in later. But basically, this is a self-time system, and the width of this depends on the ramp rate of this signal. So if I run it slower, then these basically drag out in time. Okay. In the video, what you want to look for when I change the gain is we had a big spike at about 150 nanoseconds. And if you look through the video, what you're going to look for is that the data lines are not coming in at the same time. So the reason we had this glitch when we didn't have the gain higher is that these data bits were staggered. And if they stagger in random ways, then basically they're going to add up to a number which is different from what's happening as this ramps down. Any questions?
Would the overall appearance of the output of this one change appreciably if you change the warming?
It would. I think another way to address what you're heading toward, maybe, is look at what happens when this is a sinusoid instead of a ramp. Okay, so let's just change this to sine. We have already set it up. And then go ahead and grab the data and bring it down. So now what we want to see is what is the self-timing happening when we bring in a sinusoid instead of a ramp. So what we're seeing is when the sinusoid is rapidly changing, in effect our sampling rate is faster. And when the sinusoid is slow, our sampling rate, our times are wider. We'll see that when we do testing, we're going to take advantage of that fact. We're going to make a histogram of this data coming out. And we'll see that we have many more occurrences of the data when the sinusoid is slow than we do when the sinusoid is fast. And that'll tell us the performance metric of the data. Any questions on what you're looking for here? So note the input ramp rate versus the period of the LSP signal. And basically there's a correlation between the two. Now, when I had the gain low, I could easily fix that problem if I built a register here that was clocked. And I waited for all these data bits to be valid before I clocked them into the beta 8. Right? So that's how we typically solve that problem, and we do it so much that we take it for granted when we don't have that as an option to do it. So I could ask you how the 7821, how the sample clock works as a concept question. And you would tell me that when write is low, the digital bits are allowed to write to the DAC register to send it to the op-amp inside to turn it into, it's an R2R ladder, so to turn it into a voltage. But I have this time to wait for all my data bits to line up. So that these are at the right time before I go ahead and raise chip select high and clock in that data to that register. And then that data register is what's presented to the R2R ladder and is what's presented to the op. So I wouldn't have this problem if I had clocking. But if I wasn't allowed to do clocking, how could I solve this problem? That's the challenge. So typically, you want to control the analog circuitry because this is just, it's not a feedback path, this is just a forward path. Right? So typically, we do clocking in digital because we're worried about feedback and going into invalid states. There's no feedback path here. So with clever circuit design, I can go ahead and control the timing of these bits so that they're correct. Right? So then we're back to using logical effort or the kinds of things that we talk about in digital design when we want to have these line up in time. Questions? Right, so what we want to be able to do is actually put in self-timed field. So it's not that we don't want a clock. We don't want a global clock that's running at 2 gigahertz that's running everywhere. And that's just causing all kinds of power. And remember, a clock is a wire, right? So it's just like the power wire. So you're running clocks everywhere, you have high-speed switching on the clock, you have lots of LDIDT, you have all those same kind of issues. If we could get rid of that clock and make it self-timed, we would solve a lot of problems. So you're correct, we want to build something which measures when we're done, and then says, okay, the next data bits are allowed to come through. And that's not impossible to build, you just have to be creative. It's just not typically done. Do you have a question?
The same thing, it's like the completion circuit in the asynchronous circuit.
Correct, correct. So we just need some handshaking to go on. The advantage of the self-time system is it's timed to the data coming in. So, you know, it's silly to sample a sinusoid at hundreds times faster than its frequency. All you're doing is just wasting all those samples, burning all that power. You'd much rather time it at its own natural frequency. Which again, to beat a dead horse or a living horse in biology, this is what biology does. We just don't know how it does it. Okay. I think I've covered all the questions here except the oscillator question. And I don't know. Does anybody have any questions about homework 1 and homework 2?
So going back to what you were saying about the asynchronous stack, is it possible to realize that like just no convention?
Oh, yeah, yeah, no, those circuits are just begging to be built. And I'll tell you where especially they're begging to be built is, so if we look at the end of this chapter, okay, one way that I can get high performance one way that I can get high performance out of my ADDs, and Khalil is doing it a lot for D to A's, is just hook these guys up in parallel. But because they all have to be driven off of very accurate clocks, the reason that we don't do this more often is the clocking is so expensive. The clocking is so hard to do. We could figure out how to do this with self-timed systems, and again, this is just a flow-forward path. And you can see much higher performance capability put in, right? And we'll see that a little bit with the asynchronous SAW. So that's probably the biggest breakthrough in ADCs, was somebody figured out how to take a SAR ADC, the same thing that's on our Arduino and Launchpad, that's limited to 100 kilohertz, and run them at several gigahertz, all because they did self-time. Any questions about homework 1 or 2? All right, so I have a few more minutes. So let me tell you what to look at for the oscillator. So I could ask you a concept question about how the Schmidt triggers work in chapter 2 of the manual. And I'll do this, say something about it on the video. So, one way to see this guy here is that this is basically an inverter. And what if we got rid of this resistor? What do we need this resistor here for? It turns out that this op-amp has a current limit anyway. So if we got rid of this resistor, then this capacitor would just charge at the slew rate current limit of the op-amp. And that would work, except that the Schmidt trigger is built on the outside, not the inside. So the reason we need this resistor here is because if we got rid of it, then the capacitor would be at the same voltage node as the Schmidt trigger, and it wouldn't work. Well, one way to think about how the non-inverting Schmidt trigger works is take this RC circuit and attach this to the other Schmidt trigger. So take an RC circuit here, take the capacitor back output and take it back to the input. And convince yourself that that won't work. And why won't that work? Because if this capacitor, let's say this is high, and there's an RC here, and this capacitor is charging high, then the voltage that we're sending back here is high. And if there's high on both sides of this divider, then this voltage here will never go lower than ground, and it's stuck, so it's a latch. So the only way that if I put an RC after this guy here and make it come back to this and work is if I put an inverting RC. So that if this is high, then the voltage on the capacitor is low. And this low coming back here will compensate this high here, send this voltage back lower than ground, and you'll switch state. So one way to see that is in chapter 6. Ignore this multiplier, just assume it's maxed out. So here, I have an RC, but it's a negative RC. So it comes back to this other side. When this is high, this goes low, and eventually this node changes relative to ground and it changes state. So I'll explain that again in the video. If I ask anything about that, it'll be as a concept on the exam. But if we're going to build oscillators or test oscillators, you need to know how oscillators work. And so there's many ways to do it. Any questions?